Hello, chemistry students. If you're watching this video, it's because you are moving forward into your calculations of grams to moles, moles to grams, and also using Avogadro's number. In this particular video, we're going to apply those calculations to balanced chemical reactions. So in those calculations, typically that's termed stoichiometry. Stoichiometry, I call it kind of the nuts and bolts of chemistry. It allows us to determine quantities in chemical reactions. So for example, if I want to know CO2 emissions, it's dependent on the amount of fuel I burn. The more fuel I burn, the more CO2 I produce. Stoichiometry allows me to determine the amount of CO2 produced. So we can relate the quantities in chemical reactions to basically recipes. It's very similar. It's a ratio. So we're going to use an example of a recipe to introduce the concept of simple stoichiometry. So here I have a recipe to make pancakes. 1 cup of flour, 2 eggs, and half a teaspoon of baking powder makes 5 pancakes. So if I had a dozen eggs and enough of the other 2 ingredients, how many pancakes could I make? Well, it's a ratio. I know that with 2 eggs, I can make 5 pancakes. That's a ratio. So if I start with a dozen eggs, and remember, Avogadro's number, the mole, is the chemist dozen. It just tells us a particular number of particles. So that's why I'm using a dozen eggs. If I have a dozen eggs, I have 12 eggs. Just like if I have a mole, I have 6.022 times 10 to the 23rd. And if I have 12 eggs, I can figure out how many pancakes by using an easy ratio. There are 2 eggs. I want to cancel out the unit of eggs. I put it on the bottom per 5 pancakes. And what I see is that the unit of eggs cancel, I'm left with pancakes, and I get an answer of 30. So basically, stoichiometry is like following a recipe. We don't always just have 2 eggs. We might have 12 eggs because we want to make 30 pancakes instead of 5. It's the same thing with balanced chemical equations. So how much ammonia? Well, if I'm producing ammonia in this combination reaction, again, it's a combination because there's 2 reactants producing 1 product. Just like following that recipe, I can use ratios. If I had 1 nitrogen molecule, really element, diatomic, I could produce 2 molecules of ammonia. Or if I had 3 molecules of hydrogen, I could produce 2 molecules of ammonia. But we know now that it's very rare that we're only going to have masses in the units of AMU. So it's very rare that we're going to have 1 molecule of nitrogen and 3 molecules of hydrogen. So these balance coefficients are really representing the integral part of stoichiometry, which I call mole ratios. So we're using our balanced chemical equations and our ratios as mole ratios to determine how much product is produced. So let's take a look. If I know the number of moles of one substance, then I can figure out the moles of another substance in an equation. This relationship is basically called stoich. It's a mole ratio. So let's take a look at this particular reaction. I see in 1 mole of propane, and I know it's propane because there's 3 carbons, and it's a hydrocarbon that shows that all the hydrogens are saturated. But there's 3 in 1 mole of propane, there's 5 moles of oxygen required to combust and produce 3 moles of CO2 and 4 moles of water. So what can I do? Well, I can make mole ratios. 1 mole of propane reacts with 5 moles of oxygen. 1 mole of propane will produce 3 moles of CO2, and 1 mole or 5 moles of O2 leads to 4 moles of H2O. So I can make different ratios. I could have also made the ratio of 3 moles of CO2 are produced when 4 moles of H2O. There's a lot of flexibility in these ratios. So using these mole ratios allows me to set up conversion factors. And I can use these conversion factors in what's referred to as stoichiometry, but we have kind of been doing this all along with dimensional analysis and the conversion factor method. The mole ratios will be used as conversion factors to get us where we need to go. So possible calculations. If we have a balanced chemical equation, there's two really common, calculations in the beginning of simple, what's referred to as gravimetric stoichiometry. Gravity, when we're weighing things by mass, the simple calculations are, we can go from mole to mole using that mole ratio, or we can go all the way from grams to grams, because we know that if we have the number of moles, we can convert moles using molar mass to grams and easily calculate the number of grams. Now, this is the simple stoich that we're learning in chapters 4 or gravimetric stoich. When we go to solution stoichiometry and gas stoichiometry, there's more options. This is the most straightforward and simplistic. I say there's basically, it doesn't matter if you're doing gravimetric stoich, solution stoich, or gas stoichiometry, there's basic rules that you apply to all of them. And the first rule is, you gotta have a balanced chemical equation. If you don't have a balanced chemical equation, you don't have the right mole ratio. The next thing is, because it's a mole ratio, whatever units they give you, whether it be grams or milliliters, Avogadro's number, the number of particles, whatever it is, convert it to moles. So whatever units are given, convert to moles. And then once you have moles, you can use your balance equation and the coefficients to make that mole ratio to get to the moles you want. Now, if they only want to know moles of product, you'd be done. But a lot of times they ask for something else like grams. Well, if you have the desired moles of the product, convert it to grams that they're asking for by using molar mass. So these are your basic rules. Balanced equation, convert the given units to moles, use your mole to mole ratio to get the moles of what you want, and then convert the moles of what you want to the units you want. And it follows kind of this pattern. Grams of A to moles of A to moles of B to grams of B. So let's apply it. So I'm telling you it's mole to mole, but I won't always tell you that. So if we take a look, if I have 0.58 moles of molecular oxygen, that's a given, and it reacts with excess octane, how many moles of carbon dioxide do I want? So I want moles of CO2. I'm given 0.58 moles of O2. This is stoichiometry. I'm given a certain amount of something and I want to know how much is produced. And this is the straightforward mole to mole where I could use the balanced chemical equation. So convert moles of the one substance to moles of the other. Okay. The 0.58 moles of O2, well, I go to the balance equation and I see there's 25 moles of O2, so I put that on the bottom. And I want to go to where? CO2. So I look in my balance equation and I see that there's 16 CO2 per 25 moles of O2. So I set up my ratio. I make sure my final answer has the correct sig figs. 0.58 is only 2 because that's a leading zero. This is a leading zero, so the 0.37 makes it 2 sig figs, and it's 0.37 moles of CO2. Let's try another one. If I have 0.026 moles of oxygen, how many moles of water, okay? Now, noticing they're letting me know that there's excess octane. I know this is octane because there's the 8, and it's the fuel source that's being burned. So I'm concerned with the moles of O2 to moles of H2O. So I'm going to use that same mole ratio, right? So 0.026 moles of O2, I need to go from moles of O2 to moles of H2O. So where do I get the mole ratio? My balance equation, 25 moles of O2, 18 moles of water. We're not using the 16 because they're not asking for carbon dioxide, they're asking for water. And I get 0.019 moles of H2O. Now it can be harder than just mole to mole. They might ask mole to mole, but ask for an additional step of grams. So if 1.334 moles of octane react with excess oxygen, how many grams of carbon dioxide are produced? So what do we do now? Well, we can go from the 1.334 moles of octane, and I know that this is octane because it says reacts with excess oxygen. I know this is a combustion reaction, and the octane is the fuel source. So I can go from the moles of octane, and what do I want? I want to eventually get to grams of carbon dioxide, but I can first get to moles of carbon dioxide. How can I do that? I have a mole ratio, 2 moles of octane to 16 moles of CO2. Now I wouldn't be done. Actually, I would be done if they were just asking for moles of CO2, but they're not. They're asking for grams of CO2. Now, how can I do that? Well, I use molar mass. I go to my periodic table. In 1 mole of CO2, I add it up. There's 44 grams of CO2. And now I have my setup. So moles of octane cancel. There's 2 because that's my coefficient. I go to 16 moles of CO2. In 1 mole of CO2, there's 44 grams. The units of moles of CO2 cancel. I'm left with grams of CO2. And I leave my final answer with 4 sig figs because the problem started with 4 sig figs. Let's try another one. Can we go all the way from gram to mole to gram? Yes, if you're following those basic rules for stoichiometry. So in this problem, how many grams of glucose? So I want grams of glucose. So you might say, how do I know what glucose is? Well, this is CO2, this is water, this is oxygen. By default, the C6H12O6 has to be glucose, okay? And it also tells you it's being synthesized, right? So how many grams of glucose can be synthesized from 58.5 grams of CO2, or 58, yeah. So I'm given 58.5 grams of CO2. Now the bridge between CO2 and glucose is the mole ratio. So in the middle, I can go from moles of CO2 to moles of glucose, okay? And how can I do that? Where there's 6 moles of CO2 per 1 mole of glucose. But I'm not starting with moles. I'm starting with grams and I'm ending with grams. Well, how can I go from grams of CO2 to moles? It's easy. Molar mass, the 44 grams per mole. How can I go from moles of glucose to grams? Again, I'm going to use molar mass. I'm going to add this up to figure out how many grams of glucose per mole. And I can do that fairly easily, right? Because I have the formula right there. So it comes out to, again, I need to get rid of grams of CO2 and that stoichiometry rule. The first rule is a balanced equation. I have a balanced equation. Second rule, convert whatever units to moles, okay? Grams of CO2, there's 44 grams in 1 mole. Now that you have moles of the given, go to the moles that you desire. I want glucose. So I have to go from moles of CO2 to moles of glucose. 6 moles of CO2 per 1 mole of glucose. And then I finally, once I have moles, can convert to grams. How do I do that? In 1 mole of glucose, there's 180 grams. And they get those numbers because 6 carbons, each carbon is 12 hydrogens, and then 6 oxygens. If we watched our percent composition, 6 times 12, oops, the hydrogen is 1, roughly, and the oxygen is 16. 6 times 12 is 72, plus 12, 84, plus 96 is 180. And when I do my calculations, I get 39.9 grams of glucose. Now you can run this backwards, right? You could practice this, you could pause this tape and go from 39.9 grams of glucose back to grams of CO2. You would just have to flip all the conversion factors. But instead of doing that, let's do one more practice, right? Could we start with kilograms instead of grams? Sure. We could start with kilograms because I can convert kilograms to grams using the metric system. So let's read this problem. How much nitric acid in kilograms? So I want kilograms of nitric acid. What am I given? I'm given 1.5 times 10 to the 3 kilograms of NO2. So what's pretty much the first step? I need a balanced equation. They're nice. They give me a balanced equation. Step 2, convert your given units to moles. So I need to convert the kilograms of NO2 to moles of NO2. Well, how can I do that? Well, I can convert kilograms to grams of NO2, the metric system, grams of NO2 to moles of NO2. How? Periodic table, molar mass. And now that's the bridge, that's the stoichiometry. And now that I have a balanced equation, I can use my mole ratios to convert the 4 moles of NO2 to the 4 moles of what I want, which is the nitric acid. And then from moles of nitric acid, I'm just going to keep going. Grams of nitric acid using molar mass, just going them backwards now, and convert that to kilograms using the metric system. So that would be the setup. So kilograms of NO2, 1 kilogram, there's 1,000 grams. Cancel out the unit of grams because there's 46.01 grams of NO2 per 1 mole. There's 4 moles of NO2 per 4 moles of HNO3. And then in 1 mole of HNO3, there's 63.02 grams. That's the molar mass. And then the grams are canceled out by the metric system. And I'm left with kilograms of the nitric acid. Now, when you're calculating this 1,000 and this 1,000 cancel out. You don't have to plug that in, or you don't have to plug in the 4s, but I like to write everything out so I don't make a careless mistake. A lot of people, when they start getting lazy, they don't want to write the 4, 4, and they put 1, 1, which it is 1, 1, but a lot of times they'll get so used to writing that they'll forget to look at the balanced equation, and it's not always a 1-to-1 ratio. So I would just emphasize, just write it and then you can cancel it later. So that's basically your stoichiometry. It's using a balanced chemical equation, and when you're given a certain amount of reactant, you can predict how much product will be produced by using your mole ratios. So thanks for watching. And again, if you have any questions, go ahead and leave them. And Again, thanks for being patient.